In the Sierra Nevada mountains, you can find living structures that have been growing since before the Roman Empire. The giant sequoia can reach 300 feet in height and weigh over 12 million pounds. This sheer scale is built on a streamlined genetic foundation. Unlike the coast redwood, which is a hexaploid organism with 6 sets of chromosomes, the giant sequoia is diploid. A diploid organism operates on exactly 2 sets of chromosomes, containing about 8.1 billion base pairs of DNA. That genetic code builds some of the most specialized physical defenses in the natural world. Their bark grows up to 2 feet thick and is saturated with tannins, chemical compounds that naturally repel both rot and insects, while insulating the living wood from extreme forest fires. For thousands of years, mature sequoias effectively bypassed the vulnerabilities that kill other plants. Unless it physically toppled over from shifting soil or wind, it continued to live and grow. Between 2012 and 2016, California experienced a severe hotter drought. Higher than average temperatures combined with historically low precipitation to bake the moisture out of the Sierra Nevada soil. During and after this dry period, park rangers documented a completely novel event. 33 mature giant sequoias died while still standing. There was no fatal crown scorch from fire and no human logging involved. The thick bark and chemical tannins had not been breached. Instead, the tree's internal operating system had completely shut down. This diagram illustrates the daily physical workload of a giant sequoia. To survive, a single mature tree must pull up to 1,000 gallons of water out of the ground and push it 300 feet straight up against gravity every single day. It accomplishes this without a deep taproot. 95% of a sequoia's root system lies within the top 3 feet of soil, forming a shallow mat that radiates outward up to 200 feet from the trunk to catch the slow, steady drip of melting Sierra snowpack. To keep water flowing to the very top, the tree relies on apoplastic water stored in the tiny dead spaces outside the plant cell membranes. The tree injects these water stores into its sap to maintain internal turgor pressure, the structural stiffness required to keep its massive canopy hydrated. The hotter drought severely reduced the winter snowpack. Without that slow surface melt, the shallow root mat had nothing to absorb. In response, the sequoia executes an emergency physiological lockdown. It closes its stomata, the microscopic pores on its leaves, to prevent existing moisture from escaping. This stops photosynthesis entirely and causes the internal water pressure of the tree to plummet. The tree is not starving. It simply lacks the hydraulic tension necessary to lift water to its highest branches, leaving the upper canopy completely dried out. This drop in pressure invites a secondary threat, the western cedar bark beetle, a species in the Phloacinus genus. Historically, these insects only targeted fallen or already dead branches on the forest floor. But the beetles can detect the severe drop in the sequoia's internal water pressure. This signals that the tree lacks the moisture needed to push out invading insects with sticky sap, leaving its defenses down. Instead of scavenging deadwood on the ground, the beetles fly to the top of the tree. They bore directly into the cambium layer, the thin strip of living tissue right beneath the bark of the drought-stressed upper branches. This diagram shows a cross-section of a branch under attack. The beetles carve intricate networks called galleries to lay their eggs. These galleries physically sever the tree's remaining vertical vascular pathways, executing the tree from the top down. At the same time, the dead, dry canopies act as perfect kindling. High-severity crown sires are now incinerating these mature trees entirely, burning so intensely that they destroy the cones and seeds needed for the grove to reproduce in the ash. The giant sequoia is facing a structural collapse caused by a deadly synergy, extreme climate stress disabling the hydraulic system, which allows a native insect to become lethal, followed by fires too hot for even the sequoia to survive. Fewer than 80,000 mature giant sequoias remain in their native California range. Yet 5,000 miles away, a population of over 500,000 giant sequoias is actively expanding. These trees are growing in the United Kingdom. British collectors imported the first seeds in the 1850s as exotic ornaments for large estates and botanical gardens. The British climate offers consistent rainfall and heavy fog. This provides a steady supply of surface moisture year-round, meaning the shallow root systems never face the severe water stress currently devastating the Sierra Nevada. And an aesthetic gardening trend from 60 years ago accidentally supplied the exact hydraulic stability that the species requires. To understand exactly how well these relocated trees are performing, researchers from University College London and the Royal Botanic Gardens initiated a wide-scale study of their growth capability. This visualization displays terrestrial laser scanning data, a technique using ground-based lasers to build highly accurate 3D structural models. By mapping 97 individual trees, researchers calculated that a UK-grown sequoia pulls an average of 85 kilograms of carbon out of the atmosphere every year. This bar chart compares that carbon uptake against trees in California. The data proves that the imported trees are accumulating biomass at a rate nearly identical to sequoias growing in their native mountain range. This success provides empirical backing for assisted migration. Assisted migration is a deliberate conservation strategy where vulnerable species are relocated to new geographic areas with more compatible climates. The giant sequoia's strict biological hardware is failing under the new extremes of the Sierra Nevada. Preserving the largest living structures on Earth now depends on moving them to environments where their internal physics can still operate.